All right, so today what we're going to do is put together all the things that we've been looking at on how to do statics. So let's start with a fairly simple statics problem. We're going to have just a basic triangle. We're going to have a pin on one corner, a roller on another corner. We're going to label our corners. We're going to call this A, B, and C. And we're going to have an external force of 500 pounds to the right on B. We also need some dimensions here. So let's go ahead and throw in some dimensions. We'll say that A to C is 16 feet and A to B is only, let's say 10 feet. Obviously, this isn't quite to scale. And we'll say that from C up to B, the height of our rectangle is also 10 feet. All right. Now, we're going to start out the same way we always start out. We're first going to remove our pins and rollers, and we're going to replace them with forces. So this was a pin. Oh, my bad. So this was a pin. We're going to replace it with reaction force A in the Y direction and reaction force A in the X direction. This was a roller, and it was on a horizontal surface. So we're going to replace it with a vertical reaction force. This is the reaction force at C in the Y direction. Now, our first step here is always going to be find our reaction forces. All right, so this is step one. Find the reaction forces. And to do this, we're going to use sum of forces in the X equals 0, sum of forces in the Y equals 0, and sum of moments equals 0. So we'll go ahead and write out our equations. So we'll say the sum of forces in the X direction equals 0. All right, and so what are those forces in the X direction? Well, I have this 500 pounds, and it's going to the right, so I'll call that positive, so 500. And the only other force that is horizontal in the X direction is RAX. So I'll say plus RAX. And I say plus RAX because RAX is also going to the right. Now, I have an equation right here, and I can go ahead and solve it. I'm going to move my 500 to the other side, so I'm going to subtract 500 from both sides. So I'll say negative 500 equals RAX. Now, what does this negative sign tell me? That tells me that the direction that RAX was drawn is wrong. So I'm going to come over here, and I'm going to erase the arrowhead on RAX. I accidentally erased RAY too. And I'm going to draw the arrowhead the other way. All right, I'm going to darken it in just to show that I've changed it there. So RAX is 500, but it's actually going to the left because when we thought it was going to the right, we got a negative number. All right, so that was sum of forces in the X equals 0. Now, let's do sum of forces in the Y equals 0. Sum of forces in the Y equals 0. So what forces do we have in the Y direction? Well, we have RAY, and it's pointing up, so we'll keep it positive, equals RAY. And we have RCY, so plus RCY, also positive because it's pointing up. We have no other forces in the Y direction, but what we see here is we have two unknowns, so we can't solve this equation yet. So we'll come back to it. So let's look at our third one. Sum of the moments around any point equals 0. Now, what point should we pick? I'm a big proponent of picking the point where the pin is. You almost never can go wrong that way. So let's go ahead and pick the point where the pin is. That's point A. So we'll say the sum of the moments around point A is 0. So, which forces cause moments around point A? RAX goes through point A, and RAY goes through point A. And remember, a moment is a force times the distance. If that distance is 0, the moment is 0. So we know RAX and RAY don't create any moments. Their moments 0, they don't matter. So we're left with this 500 pounds and RCY. Those are the only other two external forces. So 500 pounds, force times distance. Our force is 500 pounds. And our distance, now remember, we're measuring so that we're measuring a perpendicular line to the line that force goes through. So what is this line? We find it right here, times 10 feet. Now, is this positive or negative? Remember, clockwise is negative, counterclockwise is positive. So this 500 pounds is going to make it rotate clockwise. It's going to go that way around point A. So we're going to go ahead and put a negative sign here. Our other force is RCY, so plus RCY, and its distance, so we're still measuring from A, but we're measuring this way because that gives us a perpendicular measurement, and so that's 16 times 16 for our distance. Now, is it positive or negative? Well, it's going to cause things to rotate counterclockwise around point A, so that's going to be positive, and we'll leave it that way. Now, we just have to do the math on this. So we have 0. We have 0 equals negative 5,000 plus 16 RCY. We'll move the 5,000 to the other side. So 5,000 equals 16 RCY. I'll divide both sides divide both sides by 16. So 5,000 divided by 16 is 313. And 16 RCY divided by 16 is just RCY. So we know that RCY is 313. So I'll come up here now, and we'll go ahead and write that in. RCY is 313. That also allows us to go back to this equation. Since we know RCY is 313. So that gives us 0 equals RAY plus 313. And what we'll find is that RAY has to equal negative 313. What that tells us is that the arrow on RAY had to be wrong. We had it pointing up. It should actually be pointing down. So it's pointing down 313. This one's pointing up 313. And so far, so good. So step 1, we're finding the reaction forces using sum of forces in the x direction equals 0, sum of forces in the y direction equals 0, sum of moments equals 0. Next, we're going to draw a free body diagram for each joint. So we have 3 joints here. We have A, B, and C. So let's look at joint A. Joint A has 500 left and 313 down. but it also connects to B right here, and it connects to C. So we have what's called force A, B, and force A, C. Let's look at point B now. B connects to A and C also, and it has a 500-pound force pushing to the right. So we have force A, B. Notice I still call it AB. I don't call it BA. I always want to keep these letters in alphabetical order, so that way I know this force is the same as this force. If I start switching the letters, it can get confusing. And force A, C. And we said we had 500 pounds going to the right. Now, it doesn't matter. I can draw it here, or I can draw it here. Just don't draw it on both. So I'm going to leave it in the original side and move on to point C. So point C, we look at point C, it connects to point B. It connects to point A, and it has this external force, RCY, also pushing on it. So we'll go ahead and draw that on here. This is force B, C. Oh, my bad, I called this AC. This should be BC. All right, force BC, force AC, and we had force RCY, which was up 313. So force RCY is up 313. All right, now our next step, 3. Redraw the free body diagrams with only X and Y components. Now, many things are already only X or Y. For example, this 500 is only X and Y. This FAC is only X and Y. But some are diagonals, like force AB, need to be split. So we're going to redraw this. All right, redraw A. Let's redraw the things that don't change. So force AC, 313, 500. Now force AB is up and to the right, so we draw a force that's up. And this is force AB, the Y component. And to the right, we have force AB, the X component. We'll redraw point B also. So I have my 500 going to the right. Now force AB needs split. It goes down to the left. So I'm going to say the left component is force AB, the X component. This is force AB, Y's component. Now we have force BC. Force BC goes to the right and down. So the right part is force BCX. And the down part is force BCY. Now we have point C. Force AC is already entirely left and right, so we don't have to change it. Force AC. The 313 is entirely vertical. We don't have to change it. And force BC goes up and to the left. So we'll have force BC's Y component and force BC's x component. All right. Now, the next part is how we actually find these forces. And this relies on what we just did a lot. So I'm going to switch colors here just so we can see the changes. What we're looking for is we're going to look in the x and y direction on each free body diagram for places with only one unknown. So, for example, let's look on A, and we'll look in the x direction. So I have 500, I have FABX, and FAC. I have two unknowns. Neither of these is known. All right, so we can't do anything here yet. However, if I look in the y direction, I have force ABY and 313. There's only one unknown. Force ABY is the only unknown. And we know that it has to even out. Remember, the sum of the forces in the x direction is 0, and that's at every point. The sum of the forces in the y direction is 0, and that's at every point. So, what I know is if I have 313 down right here, to even that out, to counteract it, force ABY must be 313 up. So I'm going to darken the arrowheads in. That tells me I know the direction is correct. 313. All right. Now, if I know the direction is correct for force ABY, ABY is on here in two places. It's here and it's here. So it's on point A and on point B. So I know the direction is right. So I'm not going to change this one, even though it's up here and down here. What this means is it's pulling away from the joint on A, so it's in tension. If that member is in tension and it connects point A to point B, that means it's pulling away from both point A and point B. Kind of like if you have a rubber band and one person holds one end, one person holds the other, and you stretch it, the rubber band pulls both people. It doesn't pull one of them and push one of them. So we see the same thing here on member ABY. It's pulling point A, and it's also pulling point B. It's in tension. All right? So ABY we know is in the right direction. Not only that, but ABY along with ABX make up part AB. In fact, if we scroll up here, notice there's an AB. There's no ABY and ABX in real life. So if I know ABY is in tension, that tells me ABX also has to be in tension. And every force is on here twice. So ABX is on point A, and ABX is on point B. And they're both in tension. Now, we don't know how much they are yet, but we're working our way there. All right? Now, I should maybe say we look in the x and y direction on each free body diagram for places with one unknown, and we keep repeating this. So, let's go back. Now in the x direction on A, we still have two unknowns. In the y direction, we have 0 unknowns. All right, so we can't do anything there. But we did find ABY. It was 313. That means when we get over here on B, we can go ahead and say that's 313 also. All right. In fact, whenever you find a number, you're always going to write it on there twice because every force is shown in two different places. So now when we get over to point B, we look in the x direction, we have two unknowns. So we have force ABX and force BCX. All right, nothing we can do there. But in the y direction, we have force ABY and we have force BCY. We know ABY is down with a force of 313. What that tells us about force BCY is that it has to be up with a force of 313. All right. Now, since I switched the arrowhead on force BCY here, that means it's in compression. That also means that I need to switch it on all of the force BCs. So BCY over here needs to move down. It was originally up, so now it's going to move down. When the arrowheads are pointing towards the joint, like it is now, that means it's in compression, kind of like if we had a 2x4 and two people were both pushing on it. That 2x4 is pushing towards both of you, all right? So even though force BC goes from B to C, it pushes in on both of them, all right? So force BCY is in compression, which means the arrowhead is pointing towards the joint. So the arrowhead here, pointing towards the joint, the arrowhead here, pointing towards the joint. All right. Now, since we found force BCY is in compression, that tells us that force BCX must also be in compression because they're two different components of the same force. You can't be in compression in the Y direction and tension in the X direction. So we know if BCY is in compression, BCX is in compression. So we'll do the same thing on both the force BCX's and move them so the arrowheads are pointing towards the joint in both situations. This tells us that they're both in compression. All right, so we found a force. It's time to start over. On A, we have two unknowns in the X direction still. We have no unknowns in the Y direction. Nothing we can do there. On B, we have two unknowns in the X direction. We have zero unknowns in the Y direction. All right, and we found that BCY is 313. So we're going to make sure we write that in both places. Now on C, we have two unknowns in the X direction, and we have no unknowns in the Y direction. So we have found everything we can. The next step is when you get stuck. So when you get stuck, we're going to use similar triangles to find an X force from a Y force, or vice versa. All right, so to do this, we're going to use one of the diagonals. So we're going to use a diagonal force. So we can come up here and we can actually pick either one. And we have two of them. We have AB and we have BC. And it doesn't matter which one we use. So I'm just going to go ahead and use AB. So we're going to come down here and draw it. So notice from point A to point B, we go to the right 10 and we go up 10. So let's go ahead and draw it. So point A, point B, and this was 10 feet over and 10 feet up. All right. Now, the forces go in the same angle. So whatever this angle is, the force AB, goes between points A and point B. It also goes on this line. So whatever that angle is the same angle here. And force AB is made out of force ABX and force ABY. Now we already know one of these. If we come up here, we already know ABY right here, 313. Since this angle is the same on both of them, and since we know they're both right triangles, these are what are called similar triangles, which means they have the same ratios. So what I can do is take this number put it on the bottom of ratio, this number on the top of ratio. So the horizontal number on the bottom, here the horizontal number also goes on the bottom. The vertical number goes on the top. And you're always going to end up with one unknown, and you can always cross multiply to find it. Now when I cross multiply those two together, I get 313 times 10 equals 10 times FABX. And you would find that FABX equals 313. Now, why was it the same? It's because it's a 45-degree triangle, and this side and that side were the same angle. Okay? I want to show you that this doesn't always happen, so let's look at it if we picked the other two sides. So if we picked B and C, all right? So B to C, so if this is 16 feet and this is 10 feet, it goes over 6 feet and down 10. So if I would have done it the other way, let's pretend we didn't do it this way, although that way it was perfectly valid to do it. Let's just say we picked the harder one, and we'll show that that works also. All right, so we had point B and point C, and we went over 6 feet and down 10 feet. Now this is similar to force BC, because force BC goes from point B to point C, and force BC is made out of force BCY and force BCX. All right, this angle and this angle are going to be the same, which tells us the triangles are similar, and we can set up our ratio. So I'd say 10 over 6 equals force BCY over force BCX. Now, do we know either one of those? Well, up here, we know BCY is 313. So BCY will replace with 313. So I'll cross multiply. 313 times 6 equals 10 times force BCX. And let's go ahead and do the math on that. So 313 times 6 divided by 10, about 188. So force BCX equals 188. Now that I know this, my next step from 5, I just come around and I repeat to 4. All right, so I come back to step 4, and I know that BCX is 188. So I come back here and I find that, and I go ahead and put it in. So there's BCX, it's 188. Now remember, it always goes in twice, so BCX, 188. All right, and now I'm back to step 4, so I'm repeating again. So I'm looking for one unknown. So on A, in the Y direction, 0 unknowns. In the X direction, 2 unknowns. On B, in the Y direction, 0 unknowns, but in the X direction, I know I have 500 going right and 188 going left. How much more do I need going left to even that out? Well, I have 500 going right minus the 188 that I have going left, and that tells me I need 312 more going left. So ABX is 312. I write it there, and I'll write it here. And notice the arrowheads on these are already colored in, so I already know which direction they're going, so I don't need to worry about that. Now, I start over, I go to 4, I look for places where I have one unknown. On point A, in the y direction I have 0 unknowns. In the x direction, now that ABX is known, force AC is my only unknown. So I'm going to have 500 to the left and 312 to the right. 500 to the left, 312 to the right. How much more do I need to the right? Well, I know force AC has to go to the right because I need more going that way. And I need 188 more to the right, which means force AC is going the right direction. It's in tension. So I found it to be 188 here. So over here, it also has to be 188. Now, do I have anything left that's unknown? No. So I now would say that I'm pretty much done. My last step, so let's say number 6, put back together diagonal forces. All right. And write on original problem. So first, let's do the ones we know. So for example, force AC is 188. So when I come up here, what is the force between point A and point C? It's 188. Is it in tension? Like, is that member being pulled apart, or is it in compression where it's being squished? Well, let's come down and look at the arrow. The arrow is pulling away, so that tells me it is in tension. All right? Now, if I wanted to find AB right here, I come down here, and there is no AB. I have ABX and ABYs, but no AB. So how do I put these back together? Well, I'm actually going to use Pythagorean theorem. So remember that force AB is made out of force ABX and force ABY. And we found ABY to be 313 and ABX to be 312. I'm just going to use the Pythagorean theorem. A squared plus B squared equals C squared. So in this case, my C, so this is my A, this is my B, that's my C. So I'm going to have force AB squared equals the square root of force ABX squared plus force ABY squared. It's going to be the square root of 312 squared plus 313 squared. Let's go ahead and find that for us. And I found that it's 441. So force AB is 441. So I'll come up here and write it on. And is it in tension or compression? So let's look at the arrows. ABY is pulling away from the joint, and ABX is also pulling away from the joint. That tells us pulling away means tension. Now let's do BC. So BCX and BCY are the components. So force BC is made out of force BCX and BCY. And what are they? So force BCX is 188 and BCY is 313. So I'm again going to use Pythagorean theorem here. and I got that force BC is 365. So let's go ahead and write that on. 365. And is BC in tension or compression? So let's go ahead and look down here. So BCX pointed towards the joint, BCY pointed towards the joint. Since they're both pushing in on the joint, that's the opposite. So that would tell me it's in compression. And at this point, the whole problem is solved.